I would like to show a couple of clips from the shaking table test. So this first case is of untreated ground supporting the embankment. The shaking has begun. So it can be seen that the soil is fully liquefied and it is collapsed. This case corresponds to the ordinary column treated ground. So during shaking, the water gushing out of the granular column is able to be witnessed over here. Unlike the previous case where the soil had fully collapsed, so in this case it had performed better. So the water had come up through the granular columns. It is a case of encased granular column that is to be shown here, similar to the previous case of ordinary granular column treated ground. So the water that gushes out of the granular column is visible over here. Hi, in follow-up to the previous lecture that was titled on simulation of soil liquefaction using FLAG. So this lecture is delivered on the title of Mitigation of Soil Liquefaction using Granular Columns. The outline of the presentation is granular columns, a brief intro about granular columns and mainly the mechanism that are associated with granular columns which helps to mitigate the liquefaction, and the simulation of granular columns is illustrated using FLAG 2D, and granular column for applications such as sloping ground and for strip footing is to be delivered here, and the simulation which was performed on 1G shaking table and as well as the simulations that was performed using FLAG 3D is to be demonstrated here. Firstly, granular columns for liquefaction mitigation. So granular columns is nothing but the stone columns. The terminologies are used interchangeably. The treatment is defined in terms of area ratio. The extent of treatment is usually quantified in terms of area ratio. A term which is defined as area of granular columns, the term which is defined as area ratio is defined as the ratio of area of granular columns to that of the tributary soil. The typical area ratio adapted for granular column treatment. Area ratio is defined as the ratio of area of granular columns to that of the surrounding soil, the tributary soil. So usually the granular columns are installed either in a square pattern or in a equilateral triangular pattern. So the typical area ratio ranges between 10 to 30%. So the columns can be seen here, of circular shape, and the intermediate region is made of the native soil and into which the columns are installed. So the efficiency of the columns depends on the influence area of these columns. So it depends on the diameter of the columns as well as the spacing. So here the effective diameter of the square pattern columns is 1.128 s, and for triangular pattern it is 1.05 s. S is the spacing between the columns. Construction of granular columns. So this is usually carried out using a vibratory method. A vibratory probe is inserted into the ground and the probe is assisted by the water jets to soften the soil, and as the probe is vibrated, the soil gets densified, and once the probe reaches the desired depth, the material which is gravel, will be fed from the top or from the bottom. So that governs the top feed or bottom feed method. When feeding the gravel into the through the probe will also be used to compact the gravel. So by radially expanding the columns and densifying the surrounding soil. So through this means the surrounding soil will get densified. So it can be seen here, the gravels are filled and progressively the column is built, and here almost the column reaches the ground surface. So it is important to note the deformation mechanisms that are caused by the deformation mechanisms of liquefaction. So there are two types, of which the first one is of volumetric strains. So in case of volumetric strains, the three cases that contributes to the volumetric strain are partial drainage, sedimentation and reconsolidation. Partial drainage is the dissipation of excess pore water pressure that happens during the cyclic loading or during the earthquake loading, because the sand has got some permeability. So as a result of which some excess pore water pressure will get dissipated even during the shaking. That is about partial drainage. The sedimentation is the one which has a predominant effect in case of the level ground deposits, where when the soil deposit reaches initial liquefaction, that is RU approaches 1, so it is almost will be in a fluidized state and the soil particle will sediment, so the result of which would be a huge volumetric strain, in terms of which is the result of sedimentation is a excessive settlement, and the reconsolidation is whatever the dissipation of excess pore water pressure and the volumetric strain due to reconsolidation is due to the dissipation of excess pore water pressure that occurs after the shaking ends. Coming to the other type of deformation, that is due to the deviatoric strains. This occurs during the presence of a structure. When a ground supports a structure, there would be an effect of seismic soil structure interaction, and there will also be a bearing capacity issue. Coming to the mitigation mechanisms that are associated with granular columns, firstly the densification. So we saw that the installation of granular column will result in densification of surrounding soil. So the loose sand is more vulnerable to liquefaction. So when it gets densified, so obviously the cyclic resistance of sand increases. So in turn the liquefaction resistance increases. So in case of sand, it can be densified through the vibratory means, and this can be verified through the in situ test before the treatment and after the treatment. Say for instance, if the SPT test is conducted, the effect of densification will get reflected in terms of N value. And the other important mechanism is shear reinforcement. So this occurs because of the difference in the shear modulus between the shear reinforcement effect arises as a result of the difference in the shear modulus. The shear reinforcement effect arises due to the result of differences in the shear reinforcement effect arises as a result of the difference in the shear modulus between the granular column and the surrounding soil. Obviously the column is stiffer than the surrounding soil, and this in turn leads to reduction in cyclic shear stresses that are experienced by the soil. And this particular mechanism, shear reinforcement, the underlying assumption is the strain compatibility. So the column is expected to deform in pure shear, so thereby attracting more the earthquake induced cyclic shear stresses. Since the column attracts more shear stresses, so in turn the stresses will that are experienced by the soil will be lower. So that is the aspect of this shear reinforcement. So it is governed by the ratio GR, that is the ratio of shear modulus of granular column to that of surrounding soil. A value of between 7 to 10 is necessary to obtain a substantial reduction in the shear stresses that are experienced by the soil in order to have a good shear reinforcement effect. So this is governed by the area ratio and the GR shear modulus ratio, and this GR governs the mode of deformation of the column. So if flexure is present, if the column bends, so obviously the effect of shear reinforcement will reduce. Then the third mechanism that occurs as a result of stone column is the drainage. The column is known to have higher permeability than the soil. So normally the column is expected to have a 2 order of permeability to be higher than the surrounding soil. So it is a function of Ks, the permeability of soil, Kd, permeability of the granular column, and the fines content. So the fines content has a significant effect on the drainage capacity, as the fines could clog the drain. The clogging would reduce the drainage capacity. Focusing on the shear reinforcement effect, it is dictated by the shear modulus ratio, and the assumption is shear strain compatibility, and that is which means that the soil and granular column experiences the same shear strain. So the granular column attract more stresses from when compared to the soil. So this in turn reduces the cyclic stress ratio, which is the cyclic shear stresses that are induced in soil due to earthquake loading. And if the column is very stiff, so then it might experience the flexural deformation as opposed to the expected shear deformation. So such cases are also reported by the several researchers. So it can be seen the columns, certain region of the column experiencing shear mode of deformation and flexural mode of deformation. So the shear reinforcement effect would be better when the soil experiences shear deformation, but it would be very low when it experiences the flexural deformation. Here comes the other term, ordinary granular columns. The term ordinary here refers to the columns that does not have any geosynthetic encasement. So the homogeneity of such columns are affected by the deformation of the soil, and the fines content that are present in the native soil could possibly clog the drain, which would reduce the drainage capacity of granular columns. So these two are the disadvantages of these two are the disadvantages of ordinary granular column. The other possibility is the encased granular column. So the encased granular column is very popular in clay. Here you can see the column, it is wrapped with geosynthetic encasement. So in case of clay, soft clay deposit, it is known to increase the bearing capacity and lateral load resistance, and it has been reported by several researchers in the past. When it comes to the use of encased granular column in sand for mitigating liquefaction, so the data is very limited, and most cases it is the unit cell that in most cases the unit cell simulations are conducted to evaluate the response of encased granular column relative to the ordinary granular columns. So, having the three mechanisms of liquefaction mitigation that are key to the performance of granular column is densification. So, it reduces the liquefaction potential, that is, it increases the relative density of sand, and it can be achieved in field as a result of installation of stone column, and this could not be easily replicated in the laboratory tests that are undertaken as a model. And shear reinforcement effect, that this occurs as a result of the difference in the shear modulus between the two materials and the drainage as a result of difference in the permeability. For modeling, so the computational effort is the factor that governs the choice of modeling among the cases, the choices that are shown here. Full 3D requires a significant computational effort, and unit cell is a smaller model. It can be simulated with a reasonable computational effort, and it is possible to model in both 2D as an axisymmetric problem and in full scale 3D as well. Equivalent area, in this case the 2D modeling is possible, and the 3D slice, then equivalent homogeneous soil and the cylindrical gravel rings. So, the choice of this approach could be vary with the, so the choice of the approach depends upon the, so the choice of the approach depends upon the complexity of the problem and the computational resources that are available. So, the previous studies have considered various mitigation mechanisms. The previous studies have considered different mitigation measures, and among them it is the granular column is very limited. For instance, Adelier et al. 2003 considered a soil deposit which is made of silt that supports the footing. So, here in this case the soil is treated with granular columns of area ratio, that is 30%, and the performance of the treated ground is explored, and it is compared to the results from the untreated ground. And in the other case, it can be seen the sloping ground is considered as a structure. In the other case, it can be seen that the sloping ground is considered, and the granular column is used to treat the gentle slope, and here it is the untreated ground on the right hand side and the treated ground on the left side. It is the centrifuge model. The study was undertaken by Baranaki et al. 2018, and very recently Tisnado considered an embankment with the foundation soil that is treated with the ordinary granular columns. So, coming to the simulation of granular columns. So, now it is for a 2D model that is developed in FLAG. Here the granular column is modeled as a equivalent plane strain wall. So, the circular column is converted into a plane strain wall on the basis of equivalent area. So, it can be seen here the circular column and the equivalent plane strain wall. So, in case of the full scale treatment, so this would be the configuration of the width of the column and the spacing between the columns. So, here the soil deposit is made of Ottawa sand for the numerical model that is to be discussed, and the granular column. So both are modeled using PM4 sand, and the properties, the basic properties are listed here, and here it can be noted the difference in the permeability considered for granular columns, here K and 200 K. So K refers to the case where the permeability of the soil is same as that of granular column, but in case of 200 K, the permeability of the granular column is 2 orders higher than that of the surrounding soil. So this difference is mainly considered to account for the drainage that occurs through the granular columns. So this plane strain modeling approach is used to simulate a boundary value problem. This is originally a centrifuge experiment reported by Baranaki et al. 2018. So wherein it considered the sloping ground. So the left hand side it is treated with granular columns of area ratio 20%, and the right side it is the untreated ground. It is indeed a layered soil profile. The top layer is made of a dense sand and it is underlain by a silt, low permeability silt, and then the thicker layer is made of loose Ottawa sand, and then the bottom layer is made of dense Ottawa sand. So the 3D geometry is converted into equivalent 2D. Can be seen actually the columns are of 1.75 meter diameter, and the equivalent width of the column for 2D model is 0.75 meter, and the spacing is kept same because it is just the area is equated, area of column, and the input motion that is used is Kobe motion to simulate the earthquake loading. And here it can be seen the location of the instrumented locations, where the P refers to pore pressure transducers and V corresponds to the settlement and L corresponds to the lateral deformation of soil. First, for the untreated case, the responses are plotted here. So it can be seen that the lateral deformations, it shows a reasonable match, whereas the computed settlements V1 and V2 are under predicted when compared to that of the measurements that are made from the centrifuge tests. So this is mainly attributed to the limitation associated with the numerical model, because it could not simulate the sedimentation that occurs as a result of soil liquefaction. When it comes to the pore water pressure, a reasonably good match is achieved between the computed excess pore pressure and the measured excess pore pressure at most locations. When it comes to the treated ground, so the similar case, the similar discrepancy is spotted in case of treated ground as well, that is the underprediction of the settlements, and here the pore pressures are also affected. Here the simulation of, unlike the untreated ground, here the discrepancy is spotted in excess pore pressure as well. So the simulation based on element calibration, that is the parameters to represent the model parameters to represent the Ottawa sand, that is obtained through the element calibration, that is represented by the blue colored plots. You can see here the excess pore water pressures are very much under predicted. So it corresponds to the permeability, that is the experimental case, wherein the granular columns is 200 times more permeable than the surrounding soil. So for this, the permeability of the granular columns is reduced to 50 times instead of 200 times. So that is denoted as modified simulation, so which offers a much better prediction when compared to that of the predictions that are made using the element calibrated data. Following the sloping ground, a footing is considered, a strip footing is considered to rest on a liquefiable deposit of 15-meter thick, and here the granular columns are used here to treat the liquefiable deposit. The same numerical methodology is adapted over here. The numerical model comes from FLAG 2D and PM4 sand model. It is the constitutive model used to represent the sustained behavior of sand as well as granular column during the cyclic loading. The width of the footing turns to be 8 meter, and the seismic loading is simulated through the Northridge earthquake motion that is applied at the base of the numerical model. And as far as boundary condition is considered, the boundaries are, the left boundary and right boundaries are fixed in the horizontal direction, but they are free in the vertical direction to allow the settlement. That is the mechanical boundary condition. When it comes to the fluid boundary condition, the lateral sides and the bottom is impermeable. In the top, the pore water pressure is allowed to escape, and this is a coupled stress flow analysis, where in each time step the excess pore water pressure is generated as a result of the volumetric contractive behavior that is experienced by the sand, and on the other hand the dissipation of excess pore water pressure is also accounted. So the dissipation which happens as a result of the permeability of the soil in case of untreated ground. In case of treated ground, the dissipation would be enhanced by the presence of the granular column. So these aspects are inherent in the numerical model. So it was discussed in the previous lecture as well. So these are the properties chosen, the input parameters chosen for simulating the Ottawa sand granular column. So the HP naught is the contraction rate parameter, G naught is the represents the elastic shear modulus, ND the dilatancy surface, NB the bounding surface, so phi CV the critical state surface, and Q and R are the empirical constants that are used to construct the critical state surface. So among these, here two different cases of NB is considered, the bounding surface. So the bounding surface represents the peak friction angle. So 40 degrees and 47 degrees considered. This is to mainly explore the effect of shear reinforcement that the granular column offers. So SR1 is the property more or less similar to that of the sand, dense sand, whereas SR2 is much higher when compared to SR1. So this is expected to bring out the difference that comes as a contribution from the shear reinforcement effect. In terms of permeability, K and 200K, as mentioned previously, K refers to the permeability that granular column and the surrounding soil has the same value. 200K is the granular column will have 200 times more permeability than the surrounding soil. SR1 and SR2, it refers to the shear reinforcement effect. Coming to the computed responses in the 2D numerical model, the excess pore pressure plots are plotted here. The granular column treatment is undertaken for three different area ratios: area ratio of 10%, area ratio of 20% and 30%. So it can be seen that for untreated case, so this particular plot corresponds to the temporal variation of excess pore water pressure, that is at different times the pore water pressure is plotted, and it can be seen that with the increase in the degree of treatment, so the reduction in excess pore water pressure is quite obvious. So it can be seen the progressive reduction in area ratio of 10% when compared to untreated, and little lower in area ratio of 20% when compared to 10%, and finally the 30% area ratio offers the least excess pore water pressure among all these cases. So this is the improvement that occurs as a result of the granular column treatment, that is reflected in terms of excess pore water pressure in a temporal manner, that is with respect to time. When it comes to the depth, so the spatial variation of excess pore water pressure, so here at three different depths, 1 meter depth from ground, 5 meter and 11 meter is plotted, and it can be seen that for different area ratios the excess pore water pressure is, it can be seen that for the spatial variation of excess pore water pressure, that is here it is with respect to depth. So RU axis is plotted in vertical, and this is the distance away from center of the footing. So this is basically for the soil below the center of the footing, and at depth 1 meter for every depths, for each depths. When it comes to the spatial variation of excess pore pressure, so the plots are made in terms of depth. So three different depths are chosen. So 1 meter, 5 meter and 11 meter. So the x-axis corresponds to the distance from the center of the footing, and the y-axis corresponds to the excess pore pressure ratio. So at every depth it can be seen that the RU is quite higher for the untreated case, and with increase in the treatment for area ratio of 10, 20 and 30, the excess pore pressure reduction is evident in these plots with respect to depth as well. So the other means of expression, in order to show additional insights through the excess pore pressure ratio, these plots correspond to different cases untreated, and this is for area ratio of 20%, no additional drainage through granular columns, and this is shear reinforcement, and this is shear reinforcement 1, that is not much of shear reinforcement effect is expected for this case, and in this case shear reinforcement effect will be there, and in the last case the drainage is also included. So it can be seen that with respect to the excess pore pressure ratio, that is RU max, maximum value of excess pore pressure that are recorded during the cyclic loading. So it can be seen for untreated, it is like the entire free field region, that is the region away from the footing, is liquefied. RU is about 1, and not much difference in case of shear reinforcement 1, and the improvement is still lacks when compared to, even in case of SR2 where the, even in case of SR2 where the peak friction angle is set to 47 degree as opposed to that of 40 degree in SR1, still it does not make much differences in terms of excess pore pressure ratio. but when it comes to the drainage, when the drainage through the granular columns is allowed, it can be seen, it is obvious that it is excess pore pressure plot, it is indeed related to pore pressure ratio and the drainage. So this manifests the effect of the shear reinforcement and the drainage on the pore pressure responses of the subsoil. For the settlement of footing, it is plotted for three different area ratios, 10%, 20% and 30%. So it can be seen that the blue line that corresponds to the case where enhanced drainage is considered and the shear reinforcement effect is also in place. So in each of this case, so this blue line case, and even the interesting aspect is the red line is also not far from the blue line. So in which case the drainage is not there, but it is the shear reinforcement effect. So that also contributes for higher area ratios. So though it may not be, so in all these three cases it can be seen that for irrespective of area ratio, so the shear reinforcement effect has a pronounced effect on the settlement of footing. But the net reduction is not a substantial amount in terms of the settlement of footing in all these cases. So far only the drainage and shear reinforcement is considered, the densification was not considered. So when the densification is included, so altogether the outcome becomes quite different. It can be seen, so for this baseline correction it's not much difference with respect to untreated case. So this one corresponds to SR1 case, so where the granular columns are almost like the dense sand. In case of SR1, where granular columns have a higher stiffness, so the shear reinforcement effect is visible, and that too it is apparent with respect to the area ratio as well. So for area ratio of 30%, it is the least one among the shear reinforcement effect. When it comes to drainage, the effect of area ratio is not pronounced, and when it comes to the combination of shear reinforcement and drainage effect, so the difference that is obviously that is contributed by shear reinforcement as reflected here, and once the densification is included, that is we know that the dense sand behaves much better when compared to loose sand because its liquefaction resistance, that is the cyclic shear resistance, is high. So the reduction, significant reduction in the settlement of footing was observed when the foundation soil is said to be densified as a result of installation of stone columns. So this, even for the area ratio of 30%, and when the full drainage is allowed along with the shear reinforcement effect, so the maximum reduction in the settlement achieved was 35% when compared to that of untreated case. But when the densification of soil is included, the reduction in settlement that is obtained is 60%, which is almost twice as that of what the other two mechanisms contributes. So this highlights the influence or effectiveness of the densification. Apart from the numerical simulations that was carried out using FLAG 2D and PM4 sand as a soil constitutive model, so 1G shaking table tests were conducted to evaluate the performance of the granular columns. So this is the shaking table facility available at the Structural Engineering Laboratory at IIT Madras. It is a 3 meter by 3 meter shaking table. So can handle up to 1 g acceleration and 50 hertz frequency, and the specifications of the and the rigid box is shown here. It is fitted with grid rollers that aids the movement of the aluminum rings, that is the laminar box. So 18 aluminum rings are stacked to form the laminar box, and these laminates are separated by the roller that is present in between them to facilitate the relative movement, and in the sides thermocol was placed used, and the sides thermocol was placed along the interior periphery of the laminar container, and the plastic sheet was used to cover the interior surfaces of the laminar box prior to the placement of the specimen, that is the formation of the soil model. So totally 4 different models are considered and 6 shaking table tests were performed. So the first test is a reference test, that is just a level ground, and the second one forms the benchmark case where an embankment is placed on an untreated liquefiable sand deposit, and in model 3 the embankment is resting on a ground which is improved with the granular column, ordinary granular column, and then the fourth model is the embankment supported by the ground that is treated with encased granular column. So here geogrid is used as an encasement. So the area ratio considered was 6.5% and the square pattern was adopted. The dia of column is 100 mm and the spacing between the columns is 350 mm. So coming to the configuration of the test in plan, so the first test is just a level ground, and in the second case an embankment is there. Coming to the instrumentations, these are pore pressure sensors P12, P9 and A12, A6 are the accelerometers, and the L1 and L2 is the displacement transducers. These are the instrumented locations wherein the soil responses are tracked during the loading. Model 3 and Model 4. So Model 3 comprises of ordinary granular columns and Model 4 comprises of encased granular columns, that is the geogrid encased columns. Coming to the loading, here it is harmonic in nature and different PGA was used for motion 1, motion 2 and motion 2E. So this is the response of the geogrid to the wide width tensile strength test. So the load and elongation response is plotted here. The strain rate is 20 mm per minute, and here it can be seen the geogrid is shown here and the geogrid filled with the gravel can be seen here, and then the motions that are used to simulate the loading are motion 1, 2 and 2E. It can be seen, so 0.125 G, 0.23 G is a peak amplitude and 0.26 G for the third loading event. The sequence of the formation of sand specimen is shown here. This is construction of ordinary granular column treated sand bed. Here the PVC pipes are placed prior to the pouring of sand and the gravel is filled inside it. Then water sedimentation is the method adopted to construct the specimen here. So water is filled and the soil is pluviated and the quantity of water required to saturate the sand is calculated in prior to the formation of quantity of water required to saturate the sand is calculated, and the corresponding quantity of water is poured, and it is followed by the sand pluviation to form the sand bed, and the mold is of desired size is used to form the embankment. Here the instrumentation can be seen here, the LVDT here and the accelerometer here, and this is before the shaking event and this is after the shaking event. It can be seen the embankment is still in place without much damage, and it can be seen the excess pore. Here it can be seen that the water that escaped through the granular columns is existing at the surface. For the construction of encased granular columns, so the encasement is placed within the PVC first and followed by filling of the gravels, and it is the same procedure that followed for the construction of ordinary granular columns is followed here as well. The specifications of geogrid used are the ultimate tensile strength is 24.5 kilonewton per meter and its thickness is about 1.1 mm, and the opening size is 10 mm by 10 mm, and the secant modulus is 305 kilonewton per meter at a strain of 2%, and this is the pore pressure sensor that is used to measure the excess pore water pressure. This is a tiny sensor capable of measuring the pore water pressure up to 200 kPa. The base width of embankment is 0.6 meter and the slope is 1:1.5 and the crust width is 0.15 meter. Firstly, the excess pore pressures here P4, P1 and P7, these locations correspond to the soil that lies below the toe of the embankment. So, here it can be seen that at various locations, so here benchmark model, ordinary granular column for the first motion which is of lower intensity when compared to others, the second motion which is stronger, and M2E. M2E and M2 are same in terms of almost same in terms of the magnitude, but the number of loading cycles is higher over here in M2E. So, it can be seen here for this EGC M2E and OGC M2 will have a different trends when compared to the other ones, that is because of the difference in the intensity of loading, but overall it can be seen that for the treated cases OGC and EGC, their excess pore pressure ratio is lower. The excess pore pressure for the treated cases OGC and EGC can be seen at locations P1 and P4. The treated locations have indicated consistently lower excess pore pressure when compared to the untreated cases. The black one corresponds to the level ground, the blue one corresponds to the benchmark model, that is the embankment resting on a untreated foundation soil. The other locations such as P2, P5, P8 corresponds to the soil, the foundation soil that lies below the center of the embankment. So, similar trends can also be seen here, the untreated ones reaching more than 1 in some cases, and the treated ones, they are far lower when compared to the untreated cases. Coming to the settlement response, this is L1 is at the far field and this L2 is the measure of settlement of embankment. So, here it can be seen that the level ground has the maximum settlement followed by the benchmark model, that is also untreated case. And here the reason that the presence of embankment leads to the lateral displacement of soil, foundation soil. So it is because of which even here in Fairfield the settlement is lesser in case of the benchmark model when compared to the level ground case. Coming to the other treated cases, so it can be seen that they are far lower when compared to the untreated case, and more importantly the settlement of embankment. It can be seen here the settlement of OGC M1 and OGC M2 are compared to the settlement of the level ground. The settlement of embankment is a better indicator of the performance. So here it can be seen OGC M1 and EGC M2. It can be seen that OGC M1 and EGC M1 there is almost no difference between these two cases. So because of which the intensity is increased from 0.125 G in case of M1 to 0.23 G to M2 case, that is for OGC M2 and EGC M2. In order to distinguish the response of ordinary and encased granular columns. So in fact in encased granular columns the number of loading cycles were increased from 50 to 80 in order to further have a better view of the performance. So it is noted that the settlement of encased granular column is 26 mm for at 15 seconds as a reference time or number of loading cycles, that is OGC M2, that is it has only 50 cycles. So for the same 50 cycles, so the OGC has 55 mm of settlement and EGC has a settlement of 26 mm. Other than the shaking table test, so a case study was considered using FLAG 3 numerical model, FLAG 3D numerical model. So these are the dimensions. So the width of foundation soil in x direction is 82 meter, in y direction is 19.6 meters, and the embankment is of 18 meter wide and 4 meter height. This particular exercise is shown here to further interpret the response, the effectiveness of encased granular columns. So the geogrid is used here, that is modeled using the shell elements. So these elements are capable of capturing the membrane responses, that is it can take the tensile stresses, the membrane stresses, but not the bending. So it can represent the shear interaction between the soil and the geogrid, and this is an elastic material with no failure. So the specifications of geogrid are here. It is 1000 kilonewton per meter as a tensile stiffness and the thickness is of 1 mm, and these are the interface properties, that is with respect to the soil for geogrid element. Area ratio of 10% is considered here, and the permeability, maximum permeability difference between the soil and granular column is made to be 100 times. This is to capture the drainage mechanism, and the loading used here is an harmonic input motion of 0.3 G amplitude, and 1 Hz frequency. So here NTUA sand model is used as a constitutive model to represent the soil behavior. This is also a bounding surface model quite similar to the PM4 sand model, and NTUA sand model can capture the soil behavior at low strain as well. So for which this Ramberg-Osgood nonlinear hysteretic formulation is introduced, and as opposed to the PM4 sand model, that the tiny yield surface that exists in the PM4 sand model is not present over here. So that is what it is, vanished elastic region, so that smaller yield surface is now reduced to a point. And similarly the fabric tensor, that is quite same as what it was discussed in the PM4 sand model. It is to account for the change in orientation of soil particles like that occurs as a result of the dilation. So NTUA sand model is used for both sand and gravel, that is for soil deposit as well as granular column. It can be seen here with the lateral displacement contours for untreated ground. So there is a significant lateral deformation of foundation soil below the toe of embankment, whereas that for OGC is low and for EGC even better. So this offers a visual insight for the performance of the ordinary and encased granular columns in terms of the settlement of foundation soil. So it is plotted in terms of different combinations of the mitigation mechanisms. So it can be seen that the encased granular columns performs consistently better when compared to the ordinary granular columns. So here the response of granular column is isolated, it is plotted separately. The Z displacement, I mean the vertical settlement of the granular column. So for ordinary granular columns without the drainage aspect, so the settlement, it can be seen the central columns are experiencing more settlements, but gradually this decreases when the drainage is introduced, and further when densification is increased, I mean densification is considered, and finally all three mechanisms, that is the shear reinforcement which is inherent, and here drainage as well as densification. So the columns behave much stiffer when compared to the first case. This is for ordinary granular columns. And coming to encased granular columns, even in case of absence of the drainage, it can be seen the reduction in the settlement of granular column. The vertical deformation of granular column is manifested here, and similarly the stiffer responses in case of encased granular column as well. Coming to the lateral displacement of these granular columns, so ordinary granular columns with no shear reinforcement and ordinary granular columns with shear reinforcement but no drainage and no additional densification. So it reflects the trends that were seen in case of vertical displacement as well. So this particular case experiences the most lateral deformation x direction, and whereas the other cases performs in a stiffer manner, and the reduction in, even in this case with respect to ordinary and encased granular columns, given the same mechanisms, it is obvious the differences. It can be visually seen here. And lastly, the stresses in the geogrid. So it can be seen the tensile stresses are positive here. So it is mobilized at the exterior columns, that too at the lower half of the geogrid. So this, it is more pronounced in case of encased granular columns where only the shear reinforcement is present. The additional drainage and the densification is not existing in this first case. So, here it can be seen the greater mobilization of tensile stresses, but this decreases as the columns become stiffer, which means the mitigation mechanisms, drainage and densification, which comes from the granular columns. So, that makes the geogrid not necessarily to mobilize the shear stresses, not necessary to mobilize the tensile stresses. So, deformation behavior of OGC is better than, it was evident that the deformation behavior of EGC is better than OGC even when only the shear reinforcement is considered, neglecting the drainage and the densification. Geogrid deformation is influenced by the shear behavior of the columns. So, when the columns are stiffer, so the geogrid need not to mobilize the stresses, which means there is like the stresses are not transferred to it. So, the columns themselves behaves in a better manner, and the geogrid is seen to mobilize the tensile stresses in the outer columns predominantly for the shear reinforcement case, that is the first case. And the settlement of embankment base in EGC treated ground is 23% lower than that of OGC treated ground. So, the relative performance of ordinary granular columns and encased granular columns is demonstrated through 1G shaking table test as well as a 3D numerical model. So, coming to the summary, the application of granular columns to mitigate soil liquefaction was discussed. It was firstly the equivalent plane strain wall consideration, that is modeled in 2D, that is the structure is the level ground, the sloping ground case was considered, and followed by the strip footing that was also modeled in 2D, and the embankment case was considered in both the experimental setup as well as the 3D numerical model.